Good morning, this is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. I'm the organic chemistry instructor. So today we are going to start chapter 4, alcohols and alcohol halides. In this chapter, we are going to cover totally about 19 key points. So we are going to spend 3 different lectures to discuss 19 topics. The first one we are discussing functional groups, and then we are going to name the different compounds. We are going to discuss functional class nomenclature of the alcohol halides, and then substitutive nomenclature of the alcohol halides. And then we are going to discuss different classes and nomenclatures of alcohols and related bonding in both compounds, alcohols and alcohol halides. And then the first lecture will also discuss physical properties of both compounds. Particularly, we are going to study or recall the intermolecular forces. And then we spend the second lecture and the third lecture to further discussing about different chemical reactions. In our lecture 2, from chapter 4.7 to 4.13, we are going to spend about 30 minutes to discuss preparations of alcohol halides from alcohol and hydrogen halides, about different chemical reactions, particularly 2 types of reaction mechanisms. One is called SN1, the second type is called SN2 reactions. Both different reaction mechanisms are going to be related to the different types of alcohol and alcohol halides, such as primary, secondary, tertiary alcohols. What's the possible reactions? And then we are also going to discuss about halogenations and other different methods to convert alcohol to alcohol halides or to produce different alcohol halides. And then the third lecture, we are going to discussing particularly focusing on the halogenations of alkane to produce alcohol halides. 2 different types of halogenations. The first one called chlorination. Second one will be bromination. We are going to discuss the stability, structures of different radicals related to the selectivities. And then we are going to do a comparison between chlorination and bromination. The last topic will be stability of the cations, stability of the radicals as well. First of all, let's take a look about functional groups. Functional group is a structural unit in a molecule. This structural unit is responsible for the characteristic properties of that molecule. Also, this structural unit is responsible for the different behaviors under a certain set of reaction conditions. So your alkene, hydrocarbon, alkene, another hydrocarbon, alkyne. Because of these 2 compounds, you have double carbon bond, triple carbon bonds. Therefore, alkene and alkyne are also the examples of the functional groups. In this chapter, we are going to particularly discuss alcohol halides and alcohols. We are going to again focus on the nomenclature, stabilities, bonding, and also physical properties, chemical reactions. So based on IUPAC rule, we can name the different alcohol halides and alcohols into 2 different naming conventions. IUPAC rules allow the use of 2 different types of naming conventions. One naming convention is called functional class nomenclature. The second nomenclature is considered substitutive nomenclature. Substitutive nomenclature is preferred, however, functional nomenclature is more commonly used. So we are going to move on to the functional class nomenclature of alkyl halides. We are going to name the alkyl halides first. So in this functional class nomenclature, your alkyl group and the halides, they are listed separately in the name. And your alkyl group is going to be named as the largest continuous carbon chain. You start from the carbon which is attached to the halogens, and the other alkyl group are listed as substituents. For example, if you have CH3F, this compound is the alkyl halides. So you name these halides as fluoride, and then you start counting the carbon which are attached to fluorine. So you have only one carbon, CH3. This compound is called methyl fluoride. The second molecule, you start counting the carbon which is attached to the chlorine. You name this compound as chloride. Let's see how many carbons we have. 1, 2, 3, 4, and 5. If it's 5, this compound should be related to the pentane. You change A and E to YL. Therefore, you have a group called pentyl. This compound is called pentyl chloride. Let's take a look at the third compound. First of all, find your halides. In this case, I have bromide. The carbon connected to the bromide, carbon bonded with the bromide, will be your carbon 1. You can do this way, carbon 1, 2, 3. You only have 3 carbons if you're counting towards the left. How about the counting towards the right? You have your carbon 1, 2, 3, 4. 4 carbon give you a longer chain. Therefore, you call this butane. Change it to a group called butyl. And then this is CH3, CH2. This group, you call it ethyl. This ethyl is located in the first carbon. Therefore, you call it 1-ethyl butyl bromide. 1-ethyl butyl bromide. The very last example is the cyclo compounds. You are going to name it essentially the same way as your regular alkyl halides. So first of all, find the halides. In this case, we have iodide. You have your iodide. Count the carbon 1, 2, 3, 4, 5, 6. If it's 6, it's a hexane. Because you form a cyclic compound, you call it cyclohexane. And you change it into a group called cyclohexyl iodide. That's how you are going to name the alkyl halides based on the functional class. How about we name them based on the substitutive nomenclature? Substitutive nomenclature of your alkyl halides, you are going to use the halogens as the substituents. Your halogens, fluoride, chloride, bromide, iodide, will change to the halos. Your fluoride becomes fluoro, chloride, chloro, bromide, broro, iodide, iodo. And then you also going to find the longest carbon chain. You are going to place the halogens, the halos, in the smallest locant. Let's see the first example. So you have carbon 1, 2, 3, 4, 5. The fluorine is connected to carbon 1. Therefore, you call the 1-fluoropentane. In this case, you name this alkyl halides as alkane. And your halogens will be your substituents. The second molecule, you also name it as the longest carbon chain as the parent alkane. And then you totally have 5 different carbons. We have 5 carbons. Your Br bromo located in the second carbon. Therefore, you call it 2-bromopentane. The last one, you have totally 5 carbons, which is also a pentane. You have an aldo. This aldo located in the number 3 carbon, so you call it 3-aldopentane. So again, your carbon longest continuous chain is going to be the parent. You name it, and then you are going to find the side close to the substituents, as what you did before for the alkane. If you have 2 different substituents, such as you have a methyl, you have chloro, in this case is chloro, which one has the higher priority? So halogens and alkyl groups have the same priority. How do you name this compound? Again, you find the longest continuous carbon chain. So you have carbon 1, 2, 3, 4, 5, 6, 7. You call it heptane. And your chloro, you can put in the second locant, and the methyl on the 5th locant. You call 2-chloro-5-methyl-heptane. On the other hand, you can reverse the carbon labeling. So you can have a methyl in the second carbon, chloro connected, attached to the 5th carbon. You also can call it 5-chloro-2-methyl-heptane. In the future, if you don't have halides, you have alcohols. OH has a higher priority than the methyl, than the alcohol, and also than the halogens. If you have the same halogens, the larger the atom, the higher the priority. If you have alcohols, you are also going to be based on the number of carbons. The more carbon you have, the higher the priority will be. Now about alcohols, how we are going to name the alcohols? You also have 2 different classes, similar to your halides. Number 1, you call the functional class nomenclature. Functional class names have the alcohol name followed by the alcohol as a separate word. Your alcohol is a separate word. You name this compound as alcohol. And then your alkyl group will be named essentially derived from the alkane. Substitutive names starts with the longest continuous carbon chain, that carbon connected to the OH. The carbon bears the OH. And then you number from the side closest to the OH. And then you replace the alkane A and E with the OL. Your corresponding alkane, that A and E, will be replaced by the OL. For example, I have this CH3, CH2OH. Based on the functional group, based on the functional class nomenclature, you name this as alcohol. You count your carbon 1, 2, which is ethane, you change it to ethyl. You call it isoalcohol. Isoalcohol. The substitutive names will be, you use this ethane as your parent, change A and E to OL. So you change ethane to ethanol. Ethanol in the first carbon called 1-ethanol, number 1, you don't have to name it. You default it by 1. The second molecule, you have carbon 1, 2, 3, 4, 5, 6 totally. How do we name it? You have 2 nomenclatures. The functional class will be named this way. You start naming your carbon which connected to your OH. So carbon 1, 2, 3, 4, 5. Totally you have 5 carbons which directly connected to the OH. You call this pentol. pentane change to pentyl. On your pentyl in your carbon 1, you have a methyl. You call it 1-methyl pentyl alcohol. That's your functional class. Substitutive class, you are going to find the longest carbon chain, totally have 6 of them. 1, 2, 3, 4, 5, 6. You count from the side which with the smallest locant for your OH. Totally have 6 carbons, you call it hexane. You change hexane to hexanol, ANE2OL. Your OH, your alcohol, is located in the second carbon. Therefore, you call it 2-hexanol. People also call it hexane2O. The first one, this one is what I prefer. That's what I learned when I studied in chemistry at your age. So the last molecule, example in this page, in this case, so you have a carbon which directly connected to the oxygen. Based on the functional class nomenclature, this carbon will be your first carbon. So you, sorry for this. So your carbon 1, find the longest carbon chain, 1, 2, 3, 4. Totally you have 4 different carbons. You call this butyl. You have 2 methyls in your butyl, 1,1-dimethyl butyl alcohol. For your substitutive nomenclature, you find again the longest carbon chain, which is continuous. In this case, you have 5 carbons. When you count the carbon, make sure OH is located in the smaller locant. And then you have the carbon number 2, which directly connected to the OH. Therefore, you call the 2-pentanol. In this 2-pentanol, you have a methyl in the carbon 2. You call 2-methyl 2-pentanol. As usual, between your number and the letter, you use a hyphen to separate them. And then if you have a cyclocompounds-based cyclic alcohol, how do you name the compound? You also can name by 2 different ways, functional name or substitutive name. Let's name this as substitutive compounds. Let's see this one. So again, you start your carbon from the 1 connected to oxygen directly. So carbon 1, 2, 3, 4, 5. You found there's a 1, 2, you have an iso group, iso substituent. This iso, make sure is located in smaller locant. So you have 3 iso cyclopentanol. You call the pentane change to pentanol. This is cyclo compound called cyclopentanol. The very last one, you have halides, and you also have alcohol. Which one will be your priority? You name it as the alcohol, and your BR will be as the substituents. So you start from 1, 2, 3, 4. The carbon which connected to the oxygen, you label it as number 1. You number it first. And then your bromo, BR, bromo located in the number 4 carbon. You call it 4-bromo-butanol or 4-bromo-butan-1-O. So these compounds can be named either by the substitutive or functional group. In this case, we only showed you substitutive nomenclature. Take-home message: how do you name these 2 compounds based on the functional class nomenclature? And now we are moving on to the different classes of your alcohols and alcohol halides. For both types of classes of compounds, you have 2 types. One is called primary, secondary, and tertiary. The first one called primary alcohol halides. Secondary alcohol halides. Tertiary alcohol halides. How do you define each category? Based on the number of carbon your parent carbon connected to. So in your alcohol halides, you are going to define it as the primary if the carbon that the halogen is attached to is directly attached to one more other carbon. For example, I circled this carbon connected to the fluoro, directly connected to the fluorocarbon, only connected to another carbon, one other carbon. Secondary, I have my secondary alcohol halides, bromide. So this carbon connected to one carbon, also connected to another carbon, connected to two other carbons. So if the carbon that the halogen is attached to is directly attached to two other carbons, you define this halides or alcohol as the secondary alcohol or halides. The tertiary, this carbon, you see the red circled carbon which directly connected to the chloro. So this carbon bonded to 1, 2, 3 more other carbons. If the carbon with the halogens attached is directly bonded to other 3 carbons, this compound you call it tertiary compound. This carbon is your tertiary carbon. So that's how do you name 3 different types of alcohol halides. As we mentioned, for your alcohols, you also have 3 types: primary alcohol, secondary alcohol, and tertiary alcohols. So the nomenclature is essentially the same way. If the carbon connected to the alcohol is directly connected to another carbon, you call it primary. Secondary, the carbon connected to the alcohol contacted to another 2 carbons, that's your secondary alcohol. And then the carbon connected to the alcohol OH, this carbon connected to 1 carbon, 2 carbons, 3 other carbons, you call it tertiary alcohol. So the nomenclature or the classification for alcohol halides and the alcohol, they are essentially similar to each other. So let's moving on to the bonding. In your bond, you're going to have a carbon-oxygen bond, and also you have a carbon-halogen bonds. What happened in the alcohol and alcohol halides? So here you have your carbon-oxygen bond. This bond is made by the overlap of one of the sp3 hybrid orbital from carbon with your oxygen orbital. Normally that orbital will be your p orbital, from your p orbital of your oxygen. In your oxygen, you have 2 more groups of electrons. They are not paired. You call them lone pairs. You have 2 lone pairs of your oxygen. This part you need to be cautious. These lone pairs allow you to form hydrogen bonds, which is going to be affected on your physical properties. Carbon and your oxygen, this overlap is along the carbon-oxygen bond, along the line. So this bond is called sigma bond. It's reasonably strong. In your alcohol halides, the bonding between halogens and the carbons also through a formation of a sigma bond. So carbon sp3 orbital is going to be overlapped with your halogen p orbitals. So halogen carbon bond, they have different distances. The larger the atomic size is, the longer the hydrogen halogen bonds will be. Your chloro-bromo-iodo, so it's going to subject to the size increases from F2Cl to Br to I. Therefore, the bond length or distance between carbon fluoro will be the smallest or shortest, and then carbon chloro will be slightly bigger, carbon bromo will be much bigger, carbon iodo will be the longest one. So this kind of distance also is going to affect on the chemical reactions when this halides is going to be subject to the special reaction conditions. For your halides and alcohols, both type of functional compounds, they are going to have the polar bonds. Carbon, oxygen, they have two different electronegativity. Oxygen is more partially negatively charged, carbon is more positively partially charged. Similarly, in the halides, carbon is also partially positively charged. So that important information will be used for us to form carbocation, carbon cations. This cation formation related to your polar bond due to the polarity or due to the different electronegativity, therefore related to the polarity or dipole moment. So that part of polar bond will be very critical for us when we study the chemical reactions. And then we move on further to discuss the physical properties of both alcohols and alcohol halides. Again, intermolecular forces will be very important for you to understand the boiling point changes, melting point differences, including the densities. Generally speaking, in the halides and the alcohols, both you are going to find the dipole intermolecular forces. Dipole intermolecular forces is an attractive forces occurs between two different molecules, For your alcohol and alcohol halides, compared with the parent alkane, both alcohol and alcohol halides, they are polar molecule, meaning the dipole attraction will affect on the boiling point and the melting point correspondingly. If you have propane, this propane is a non-polar molecule. If you have fluoroethane, so 1, 2, 3, so 1, 2, 3 carbon, 1, 2, and plus a fluoro. So these molecules, they have very similar molar mass. The size is also very similar. Your question could be, why this propane has the lowest boiling point? And then when you replace one carbon CH3 by fluoro, you are expecting increasing dramatic 10 Celsius temperature increasing in the boiling point. What's the reason? The reason because the intermolecular forces. In this case, you have polar molecule, dipole attraction is the major reason. But if you have ethanol, so one of the CH3 replaced by OH, what you found, the temperature increased from -44 Celsius all the way to 78 Celsius. Your ethanol is a liquid in the ambient condition. Its boiling point is about 78.5 Celsius. The question is, if you have this dipole intermolecular forces, the temperature is not supposed to be increased so exponentially. What's the reason? There's another intermolecular forces called hydrogen bond. Again, hydrogen bonding is not a bonding, it's an intermolecular forces. If in your molecule you have oxygen directly bonded to hydrogen, if you have a nitrogen directly bonded to hydrogen, fluorine directly bonded to hydrogen, and then you have other molecules. So this hydrogen is going from one molecule is going to form a hydrogen bond between oxygen from another molecule. This way you form a hydrogen bond. This hydrogen bond is much stronger. Compared with covalent bond, intermolecular forces is 1/10 to 1/100 of your intermolecular forces. It's relatively weak, but hydrogen bond is much stronger intermolecular forces. Due to this stronger intermolecular forces, hydrogen bond, so your ethanol has much higher boiling point. So in this case, if you have your alcohol, your hydrogen's end is much more positive. It's called partially positively charged. This partially positive hydrogen is going to be attracted by the partially negatively oxygen. So these two molecules in between you form a hydrogen bond. You use the dashed line to represent intermolecular forces. You use a solid line to represent the covalent bonding. In this hydrogen bond, your oxygen, this oxygen is termed as a hydrogen bond acceptor. Oxygen from another molecule is termed the hydrogen bond acceptor. Your OH hydrogen, this hydrogen is termed the hydrogen bond donor. This one is a donor. And the oxygen from another molecule is considered hydrogen bond acceptor. So let's move back to the ethanol. Your ethanol molecules, you have a OH, and this hydrogen is positive end, partially positive end. Your oxygen is partially negatively end. Let's use this ball and stick model. Ball and stick model showing you the hydrogen bond formation between two ethanol molecules. So what you see, the hydrogen from one molecule, is going to be forming a hydrogen bond with oxygen from another molecule. So your hydrogen, the hydrogen by itself is considered the bond donor, hydrogen bond donor. Your oxygen, this oxygen is considered the hydrogen bond acceptor. Also, I have this a space filling model to show you the hydrogen bond formation. This second model, so-called space filling model, this model gives you the ideas about the electrostatic potential for the hydrogen bond formation. If you see more blue color, usually you represented a little bit more positive, partially positive. You see redder color, meaning partially negatively. Partially negative or partially positively charged ends, they are tending to attract to each other to form the hydrogen bonds. So again, due to the hydrogen bond formation, so make your ethanol or methanol has a larger or higher boiling point. Your hydrogen bond, I believe, is much weaker than the covalent bond. It's 1/15 to 1/20 of your covalent bond. Hydrogen bonding in your organic compounds must be involved in hydrogen and also must be involved in one of these three: oxygen, nitrogen, possibly fluoro as well. So fluoro, nitrogen, oxygen, three are different items. They must be also existing. This table showed you some boiling point for the different compounds. So you have methyl halides, isopropyl pentohexyl halides, and related alcohols. This table gives you the idea. So why you see some differences in terms of the boiling or melting point. So one more point you need to pay attention is about iodine. Iodine is a highly polarizable item. So therefore, the the dipole-induced dipole may be stronger. So why this iodine is highly polarizable? Because your valence electrons of your iodine is far away from the nuclear, meaning the nuclear attraction, net attraction to the valence electron is weaker. Valence electron can be moving around more freely, so resulting in the high polarization of your iodine. So let's take several examples about the highlights. If you have a methyl chloro, one chloro, okay, or chloromethyl, you replace two hydrogens by chloro, you have dichloromethyl, replaced by three chloros, trichloro or tetrachloro. What's going to happen? Initially, this chloromethane or methyl chloride, there's only one hydrogen has been replaced, and then you see this sample is still a gas, and then two chloro replaced hydrogens. So your temperature dramatically increased to 240 Celsius. So what we found, increasing the number of your halogens, so the boiling point is going to be increased accordingly. What's the reason? Because your induced dipole attraction has been increased. And also you can consider another way. Whenever your hydrogen has been replaced, the molar mass becomes larger. Increase the chloro, replacement of the hydrogen has been increased. The number of hydrogen has been increased by chloro increases, will corresponding to the molar mass increase. Therefore, your boiling point was found to be increased as well for most of the halogens. However, your fluorine has a special case. Fluorine has a very low polarizability because your valence electron is closer to the nuclei. The nuclei are attracted to the electron very solidly. Therefore, the boiling point does not increase with the increasing number of fluorine atoms. So let's see, if you have fluoroethane, difluoroethane, you do see the boiling point increase, and when you increase furthermore trifluoroethane, your boiling point decreases. If you have a hexachloromethane, ethane is ethane, 2 carbons. So hexafluoroethane, the boiling point further decreases. So again, this irregular boiling point trend is resulted from the low polarizability of your fluorine. Fluorine is different from your chlorine, bromine, and iodine. Due to its low polarizability, the boiling point of chloro-replaced alcohol halides will not follow the general rule. The boiling point may not be increased with the number of fluorine atom increase. On the other hand, we do see an increase and then decrease with the number of fluorine increase. So just be very cautious. Polarizability is another important point. And the second property is about solubility. Most of the alcohol halides, you can say 100% is not soluble. They are insoluble in water. On the other hand, the alcohols can be soluble in water depends on the alcohol group. Usually the smaller alcohol group is, the higher the solubility is. If you have methyl, normal propyl, isopropyl, these alcohols, 3 carbon or less, these alcohols, they are totally miscible in water, meaning you can form a homogeneous solution, aqueous solution in any proportion. When you increase the number of carbon CH2 groups, so such as if you are going to have your 1 octanol, so you have 8 carbons. In this case, 2,000 milliliters of water only dissolve 1 milliliter of octanol. The reason is your CH2, this unit is considered hydrophobic. So therefore, hydrophobic does not like water, the solubility will be decreasing. Another reason you need to consider the solubility rule, which called like dissolves like. Like dissolves like solubility rule also tells you what's the reason. And the third property is the density. The density for the smaller alcohol halides, such as alcohol fluoride, alcohol chloride, they are usually less dense than water. If you put them together with water, you mix fluorides and chlorides. So you are going to see your organic compounds going to be floating on the surface of water. The larger alcohol halides, bromides, and iodides more dense compared with water density. And also, if you have your chlorides, if you increase the number of the halogens, so the density will be correspondingly increased, such as if you have dichloromethane. So this compound has a higher density than 1. So these several examples give you the ideas. So most of the halides, fluoro-chloro-based halides, they are less dense compared with water. Bromide, iodine-based compounds have higher density, generally speaking. And then we are going to moving on to the preparation of your alcohol halides. You can have several different ways to prepare alcohol halides. What we are going to working on will be preparation of alcohol halides from alcohols and hydrogen halides. So from chapter 4.7 to chapter 4.13, we are going to spend one lecture to discussing all these different chemical reactions, except the alkane halogenation. So we are leaving it for the third lecture. Let's call it a day today. You have a wonderful day. Stay safe and stay healthy. Thank you so much.